So this is the data dependence graph. And last time we computed for each instruction in the graph what we call the critical path distance. So the critical path for this is 4. In fact, for this it's 0. For this it's 1, 7, and this is 5. This is 4, and this is 2. Okay? And with the critical path distance, we computed a schedule that is, so let's put the schedule here. In cycle 1, we put E because it has the highest critical path. In cycle 2, we put D. And in cycle 3, we put B or F. Is F ready in cycle 3? No, F is not ready in cycle 3, so we cannot put it in cycle 3. So in fact, we put B. And in cycle 4, we put F. And in cycle 5, we put A. In cycle 6, we put C. In cycle 7,
was a stall.
Yeah, we couldn't put anything because nothing was ready here. So in cycle 7, the ready list was empty. And in cycle 8, we put G. And this is a schedule that uses 8 cycles, as opposed to how many cycles for the original program order?
14.
14, yeah, compared to 14. So this saves a number of cycles. And again, this is a simulation that the compiler does at compile time. And the accuracy of this simulation depends on the accuracy of the machine model to how accurately the compiler is modeling the processor. This is clearly a simple machine model. We are assuming a single issue machine, and we are assuming that we know exactly what the latencies are. But real machines are going to be multiple issue. You can issue multiple instructions in each cycle, and the latencies are not known precisely. Usually there is a range of latencies for some of the more complex instructions. But given this model, this is what we have. An important note about this is that we are assuming here that we are doing instruction scheduling within a basic block. So instruction scheduling is done within a basic block. So using the same terminology that we used for register allocation, would this be local or global?
Local.
Local. So this is local instruction scheduling. Local within the basic block. Now, global instruction scheduling, in fact, we will not cover global instruction scheduling in this course, but we will just talk about it now for just to point out some of the complexities in global instruction scheduling. In global instruction scheduling, there are complexities. For example, if you have this basic block and this basic block, and here's an instruction I, or in fact, it will be, so let's do this like an if. So if you have an instruction I in this basic block, in order to move it, so if we were to do global instruction scheduling, we would like to have the flexibility of moving I to this basic block, for example. But this will not always be this will not always be legal, right? Why is that? Moving I here from this basic block to this basic block will not always be legal, will not always generate correct code.
Yeah, because you don't know, because what I might affect, and considering it's in the one before it splits, you probably have to add it to the other one too.
Yes, and it may be it depends. This is a condition, right? So if with this basic block, this is you are checking some conditional branch.
It may, because if it was before.
If some condition, then do this, else do this. So this is the then, and this is the else.
Right. If it needs to do something that's checked for by the condition, you move it after the condition, and the condition's not going to have the correct check.
Yeah, exactly. So it may be that I, when you do I here, when you move it here, I will have, assuming that the data dependencies are honored. So we are assuming that all the data dependencies are captured by the data dependence graph. Then if we move it here, now this basic block, the then will be executing the I, but the else will not be executing the I. So here the I will not be executed all the time. So with a motion like this, you may want to copy I in both basic blocks. So this is one complexity. And now if you do the motion in the other direction, so suppose that I have an instruction J here. So moving J from this basic block to this basic block, again, will not always be legal, because J should be executed only if the else is true. And if you move it here, you will be executing it anyway, whether the condition is true or false. And this may not be legal unless the J is going to be harmless for this path. So we're not here trying to understand or describe an algorithm for global instruction scheduling, but I'm just trying to point out some of the complexities that arise when we do global instruction scheduling. And that's why some production compilers do not implement global instruction scheduling. They only implement local. And one of them is the LLVM compiler. The LLVM compiler does not implement global instruction scheduling. It implements local instruction scheduling. So, so now we are 100% focused on local instruction scheduling. So we did this last time, and we started discussing the algorithmic details. So now we understand the concept behind this critical path list scheduling. Critical path list scheduling. And now we would like to understand the details. And one of the details is the notion of the dependent count for each instruction or for each node in this graph. In fact, let's try to think of the data structure that we need for each instruction. So if we have class instruction, what do we need to keep in this? So one of the entries, one of the data fields in this is going to be the depth count. What else do you think I need to store for each instruction, to track for each instruction in this algorithm?
The cost for the priority.
OK, so the dependent count, the critical path distance. Yes.
Yeah, CP did, yeah.
And what else?
What nodes are connected to it?
Well, yeah, so that's part of the graph representation. So the graph representation, remember in your data structures class, graphs, there are multiple ways of representing graphs. Can you remember one of them?
Array, tree.
How do we represent graphs? There are two representations at least. two common representations of graphs. There are adjacency lists. Do you remember adjacency lists?
In the matrix.
Yeah,
So
matrix.
adjacency lists. So this graph will be represented as an adjacency list. In fact, if we draw the adjacency list representation of this, now the whole point in today's lecture is to think algorithmically about this. So we understand the concept, but in today's lecture we will be trying to understand the algorithm, the actual algorithm. So the adjacency list is going to have here A. In the adjacency list, there will be an array of nodes A, B, C, D, E, F, G. And what will we have for each node here? We will have the list of neighbors. So for A, it's going to be C. For B, the neighbors or the dependents in this context are C. For C, what do we have here? G. For D,
F.
F. And for E, F. And for F, we have G. And G doesn't have an adjacency list. So this is the adjacency list. Of course, this is a simple example. So the adjacency list of each node has only one item in it. But in general, it will have multiple items. OK? So now, OK. So how does this the list scheduling algorithm start? What's the first step? So it's based on the notion of the ready list.
Yeah.
So OK. So let's write the code here. List scheduling. And first, create a ready list R. And what was the other list that we used in the example last time?
The active list.
The active list, yeah. A ready list R and an active list A. OK. So initially, what does the active list have and what does the ready list have?
The ready list has nodes that don't have any other nodes pointing to them.
OK. So remember the dep count equals 0. Dep count equals 0. So the nodes that have a dep count of 0. So, well, first of all, we have to compute the dep counts. So this step, compute dep count for each node. Now this, we are writing this as a single line, but there is an underlying algorithm here. How would you compute the dep count given this adjacency list representation of the graph? So this is an adjacency list representation. How would you compute the dep count for each node given this adjacent? So look at this adjacency list. So the dep count is, let's write it in red. So here it's 0. For this, it's 1. For this, it's for this, it's 0, 0, 0. For C, the dep count is
1.
No,
2.
2. It's dependent on 2 other
Oh, okay.
nodes.
Yeah.
OK, so dep count equals 2. Dep count equals 2.
And that one's 2.
Dep count equals 2. OK. Now how can we calculate the dep count?
Just count the occurrences
Yes.
in the list.
Yeah.
Count what?
The occurrences of those in the list, of each node in the list.
Yeah, exactly. So it's the number of occurrences of each node in the adjacency list. So we'll have to go through the adjacency list and count how many times each node appears on the in one item in one of the lists. So C appears twice, F appears twice, and G appears twice. and other nodes do not appear at all in the adjacency lists. So these are the adjacency lists. Right. Okay. So there is an underlying algorithm. In fact, what would be the running time for this? Compute the dependent count for each node.
No way he said n.
No.
Oh, wait. Well, n squared.
Well, this is n. So assuming that n is the number of instructions,
So it would have to be n squared.
it's not that bad. No. So it's n. What's the total number of items in all adjacency lists?
Just the number of edges.
The number of edges. Yeah, exactly. The number of edges. So in fact, the running time for doing this is going to be, well, if v is the number of vertices, v number of
Yeah, v.
vertices, e is number of edges. So in fact, compute the dependent count for each node. This is going to be O of v plus e.
Yeah, v.
Okay. Now we compute the depth count. Then what's the next step? For each node whose depth count is 0, we add it to the ready list. So for each instruction, let's call it op, if op dot depth count equals 0, then r dot add of op. Add op to the ready list. Okay? Now we have the ready list, the initial ready list. Then we will have to go through the ready list. We keep looping, and we pick one instruction from the ready list. So we will have a big while loop. While, what should be the termination condition here? What should be the termination condition? So we should keep looping as long as
The ready list and the active.
yeah, exactly. So in fact, if the ready list is empty, that's not a termination condition, because here we have the ready list empty, but we're not done yet.
Yeah, 'cause
In fact, you can just count the number of instructions that you have scheduled. So one way of doing it is counting how many instructions you have scheduled, and when that number is equal to the total number of instructions, you are done. Another way of doing it is looking at the ready list and the active list, and if you terminate when both are empty. If one of them is non-empty, you keep going. So while r or a is not empty, one of them is not empty, we loop. Now, and here, I'm using indentation to indicate what's inside the loop. So I'm not going to use braces. I will use indentation to indicate what's inside the loop, which is typical pseudocode convention. Okay. Now, what do we look at the ready list, right? So if r is not empty, we pick an instruction from the ready list. Now, what do you think would be the natural implementation of a ready list here? What would be the natural implementation?
Priority queue.
Yeah.
Yeah, priority queue, exactly. So this, conceptually, this is clearly a priority queue, because you have these ready nodes, and each one has a number that indicates their priority. So this is exactly what a priority queue was designed for. So we will assume that R is a priority queue. So R is a priority queue, while A, we don't have the notion of an order or a priority within A, or a ranking within A. So A can be just a simple list, just a list, unordered list.
It could also be a small hash table too.
No, why complicate things? It can be. Well, it can be. It can be. You can make it the most sophisticated data structure ever, but we don't need it. You know, we're here. What I'm trying to say is that this is an unordered list. We don't have the notion of a priority or an ordering, so we use the simplest that works. You know, always when you design data structures, you use the simplest data structure that can get the job done. Okay. And if R is not empty, then we extract the maximum from the ready list. So we do op equals R dot extract max. So extract the node with the maximum priority number. So in this case, you know, the key for our priority list, for our priority queue is going to be these numbers in blue. The numbers in blue are going to be the keys for the priority queue. So if R is not empty, extract the max. And then what should we do with it? We extract it, we schedule it. So we schedule it, so we should have here the cycle for each instruction. So we set the cycle. We say, OK, op dot cycle equals current cycle. Now we discover that we should track the cycle number. So we will add this. Yeah, let's put it in the beginning. So here, or we can put it here. Cycle number equals 1. So op.cycle equals cycle number, or let's call it current cycle. Current cycle would be a clearer name. Current cycle. So op.cycle equals current cycle. Okay. And then what should we do with it? Now we're scheduling this.
So add it to the active list?
Exactly, yeah. Yeah, so a dot add. It doesn't matter where we add it. A dot add of this op. OK, so now we have scheduled this. Now, in order to make progress in this algorithm, what do we need to do?
Increment the cycle.
Increment
the cycle.
OK, so now after we do this, so here, current cycle plus plus. OK, and after incrementing the cycle, what do you think we should be doing next?
Check if any instructions are done.
Yeah, exactly. So we check if any instruction is done. And an instruction is done. So for each. So now to check if any instruction is done, which instructions should we be checking?
What's on the active list?
Exactly, the ones in the active list. So for each instruction op in A, in the active list. So now what's the condition for done? What's the condition? Well, how do we know that it's done? So for example, E is going to be scheduled in cycle 1, and it will be done in cycle 1 plus 3, which is 4, right?
If the current cycle equals the cycle done for the.
OK, so for the current cycle, which is when the current cycle becomes 4, and what is 4? 4 is equal to the cycle in which we put E, which is 1, plus
It's
Latency.
latency. So now we realize that we need to have the latency. OK, so I'll just put the latency before the cycle latency and then cycle. Okay, latency. So if up dot cycle plus up dot latency, the cycle for up plus the latency for up equals what?
Current cycle.
Current cycle, exactly. Equals current cycle, then this is done. So we remove up from, we can say that A dot remove it from the active list. And then what's the important thing that we need to do?
Oh, we need to see if there's anything else ready.
Okay, yeah, if it makes something else ready. So the completion of one instruction may decrement the depth count of its dependence. So we have to go through its dependence. So now, for each successor or neighbor, no, let's call it successor. For each successor up, successor S of up, for each successor S of up, we do S dot what? Depth count minus minus. Okay, so now when we get to cycle 4, we decrement the depth count of f by 1, which means that one of the instructions on which f depends has just completed. So the dependency has gotten reduced by 1. So we look at the successors, and s.depth count is decremented. Then
Add S to the ready list.
If it's depth count is 0.
exactly, only if the depth count is 0, because here, if the depth count becomes 1, it's not ready yet. So an instruction may depend on many other instructions. In general, this is the S, this is up, this is up, and this is S, the successor. And the depth count may be a big number, so it could be 5. And there are 4 other dependencies. So this up is going to decrement it to 4. Then it will be, when all 4 are done, S will become ready. So for each successor S of up, S.depth count minus minus, if S.depth count equals 0, then R dot add S or up. Should we add S or up?
S.
S. Okay. So that should do it. So this is the algorithm. So this is what this will allow us to keep updating the ready list. Okay. So now let's try to analyze this algorithm. Now the running time of this algorithm, now assuming that the data dependence graph is already there, has been computed. Well, in fact, we didn't talk about the critical path in this case. So in fact, what is missing here is compute the critical paths for each. Compute dependent count and critical path. And in fact, even if we compute the computing the critical path, as we said last time, it's going to be a DFS, and it will be another V plus E. So dependent count and critical path, each one of them is going to be V plus E. So the total asymptotic complexity for this is V plus E. Okay, so it's not going to add to the asymptotic complexity, right? Because it will multiply it by a constant. Now, for each instruction up, so what will be the asymptotic complexity for this loop?
It'd be V.
Just OV.
V, but adding to the priority list.
Oh.
So this depends on the implementation of the priority queue. So if we assume that the priority, what's a typical implementation of a priority queue?
And log in, I think.
Heap, yeah. Heap is probably the most common implementation of a priority queue. By the way, sometimes other implementations may be more efficient. You know, for example, in Dijkstra's algorithm, if the graph is dense, an unsorted array will work better than a heap. But let's assume that the priority queue is a heap. Is implemented as a heap. For the heap, the add and extract operations will take, what's the running time for add and extract? So in fact, add or insert and extract max. This is the name, extract max or DQ. Well, let's just call it extract max. So what's the running time for each of these heap operations? Yeah, it's log in. So each one of them is log in. This means that what we have here is, because this is a heap, this is of V log V. Okay? Because we do it for every op. There are V ops. And this is log V for each in the worst case. Yeah. In the worst case. But in general, it will be much less because, it will be much less because these root instructions typically will be a minority, a small subset of the instructions. But in the worst case, it could be that all of them are. So this is a worst case estimate. Now, the loop itself, the number of times this loop is executed will be what?
It's V, right?
What's that?
It's V times.
It could be more. So here, in this example, it's more than V.
Oh, because stalls.
Yeah, there are stalls. Yeah, so in fact, it's V. If you want to come up with an upper bound on the number of executions of this loop, how would you compute an upper bound on the number of executions of this loop?
Just find the biggest latency and multiply it.
Yeah, exactly. The biggest latency multiplied by the number of operations. But asymptotically, what will that be? So if the maximum latency, so if it's V times maximum latency, what would that be asymptotically?
It's still V.
It's still V. Why? Because maximum latency is a constant. And why is it a constant? Let's make sure that we understand why it's a constant. What does it mean for a certain parameter to be a constant in an algorithm? The maximum latency is a constant in the sense that it does not depend on the size of the input. In other words, it does not depend on the size of the data dependence graph. The input to this algorithm is this data dependence graph. And the size of this data dependence graph depends on the number of nodes and the number of edges, and it has nothing to do with the maximum latency. The maximum latency is a property of what?
The machine model.
The machine model, yeah, the target machine. So it depends on what instructions that machine has. What are the instructions and what's the maximum latency instruction? You know, for example, typically a divide instruction will have a latency of 6 or 8 or 10. So the latency, this maximum latency is not a function of the input size. It's a function of it's a parameter, it's a target machine parameter, which means that we can think of it as a constant. No matter how big the input graph is, the maximum latency is not going to change. So we can think of it as a constant, which means that this loop will get executed O of v times. Okay. Now, now let's look at what's inside. So here we have, every time we look at the ready list, if the ready list is not empty, we will do this. We'll do the extract max. So this extract max will take log v, right? So this is, this by itself is log v. And throughout so this is each one of them, each extract max is log v, but overall, in aggregate, throughout the execution, the whole lifetime of the algorithm, this is going to be v log v. Right, so this thing will get executed v times. Okay. Now a.add, this is constant because the active list is unordered, so we can insert in any order. It doesn't matter. Now here, when we look at the active list, how many times will we be doing this check for each instruction?
Well,
this checking for each instruction, if it's active or not, or sorry, if it's done or not, how many times will this checking be done for each?
v times the size of A.
V times the size of A. Well, the size of A is dynamic. It keeps changing.
Yeah.
No, let's, OK. The question is, for any given instruction will be in the active list at some point. How long, for how many cycles will an instruction stay in the active list?
For our model, 4.
Yeah, well, it depends. Yeah, for the latency of that instruction. So the time that an instruction stays in the active list is dependent on the latency of that instruction. So for an upper bound, an instruction will stay for a number of cycles that is less than or equal to the maximum latency. And the maximum latency is a constant. So this means that this checking will be performed O of maximum latency times v.
Which is still v.
Yeah, exactly, which is still O of v. Yeah. So let's put the aggregate here then for this. Let's put the aggregate, which is v log v. So we are putting the aggregate number of executions. Aggregate means the number of times it's executed throughout the entire algorithm. OK. Now, for each successor S of P, now this particular line, for each successor going through the successors, how many times will this get executed? What is this dependent on? So throughout the entire algorithm, how many times will this get executed? This particular line.
Every time something gets removed from the active list.
OK. Well, not
dynamic with.
Yeah, well, when we remove it, we go through all successors, right? So for E, we go through this. For D, so how many times will this line get executed?
However many elements are in that adjacency list.
Yeah, exactly, which is the number of edges. Yeah. This is the number of edges in the graph. This is E, the number of edges in the graph. So this is going to be O of E. Okay. All right. So this is E. But if depth count equals 0, when depth count becomes 0, we will add it to the ready list. Right? Now, how many times will this get executed? So this is going to get executed E times. But the addition to the ready list, how many times will this get executed for each instruction?
Just once.
Once. An instruction becomes ready once. So this is going to be, what's the aggregate running time for this line?
Oh, V log V.
Yeah, V log V, exactly. So this is going to be V log V. So then what would be the overall running time? So obviously we can ignore the V's. We have lots of V's log V's. But are these V's log V's that we have, are they additive? Should we add them or multiply them? Yeah, so this V log V, I mean, is this V log V within this V log V, or it should be added to it?
It's add.
It's add. So in fact, the relation between the V's log V's is additive. And when you add a V log V to a V log V, in asymptotic notation, it gives you a V log V. Asymptotically, this is V log V. So the V's log V's will give you one V log V, but you still have an E. Now, is the E greater than or smaller than a V log V? Will the E be greater than or smaller than V log V?
Price greater.
Well, in fact, it depends. It depends on what?
How many? The ratio of edges to nodes.
Yeah, it depends on how dense the graph is. It depends on the density of the graph. So if the graph is dense, E is going to be greater than V log V. If the graph is, what's the other kind of graphs? Sparse. If it's sparse, then E may be smaller than V log V. So which one is greater, E or V log V, depends on whether the graph is dense or sparse. So that's why, in general, we just add them. So the overall asymptotic complexity is O of E plus V log V. Because it's not clear which one is greater. Which one is greater depends on whether the graph is dense or sparse. Okay, so I wanted to go through all of these algorithmic details because the point that I'm trying to make here is that a compiler is a program that consists of a number of algorithms, and these algorithms have to be efficient in order for the compiler to compile the code efficiently within reasonable time. And so algorithms is the foundation of computer science. So everything in computer science is built on algorithms and theory of computation. In fact, the front end of the compiler is built on theory of computation, and the back end of the compiler, all of these graph algorithms, they are built on algorithms. So the foundation of computer science is algorithms, data structures, and theory of computation. And everything else is built on top of these, including compilers. Okay, and yeah, so any questions on this, this analysis? Okay, no questions? Okay, so now all of this minimizes the number of cycles. But what about register pressure? So do you remember the notion of register pressure? So is this this schedule, is it good or bad from register pressure point of view?
Bad. Bad.
Why is it bad?
Because 1, 2, 3 requires 3 registers right away.
Yeah, exactly. Yeah. So they require 3 registers, but we can do 2 registers only. But in fact, in this case, can we do this with 2 registers?
Not without spilling.
Yeah, well, with if we have 2 registers, can we do this whole thing with 2 registers?
Yeah.
Don't think so.
No. Well, you can use 2. Suppose that we do these. So we need a register for this and a register for this. Then we need a register for this and a register for this. But in order to do these 2, we have to store the result of this in a register. So we need at least 3 registers, right? So we can do this computation and this. This is 1 register, 1 register. Then we'll have to store the result in some register before we can do the other branch. These. We need a register for this again and a register for this, and then we need to store the result of this in a register. So it's you cannot do this in less than 3 registers. But again, this schedule was not looking at register pressure. So this this algorithm was only looking at minimizing the number of cycles. It wasn't looking at register pressure. Now, if we were to take register pressure into account, how should we do this and where? What should we modify?
I would assume it'd be in the while loop.
Do we change the critical path, like what we represent with the critical path?
Yeah, so we changed the priority scheme. So our priority scheme